Here's the actual algorithm, right? So I have my initial guess for my parameters. What should my initial guess be? So this actually turns out to be a little bit tricky. In these problems, the convex problems, it's not going to matter. When we start to deal with really interesting models where they're non-convex and we sort of, all the guarantees we once hoped to have about these algorithms start to kind of disappear for us, we actually have to be a little bit careful about how we choose our initial parameters. Okay, so we pick an initial vector. In our case, we'll just choose all zeros. Then we're going to iterate this procedure until convergence. And the procedure is take my previous weight, or my previous vector, my previous parameters, and subtract rho. This is going to be my learning rate. Let's just say this is 1 for now. So I'm going to subtract my gradient of the loss evaluated at my current parameterization. Okay. So rho, I said, is 1. And in fact, we'll work through some examples where we just use 1. In nice behaved problems, it's going to be okay. When we start to think about things that are not strongly convex, we're going to have to be a little more careful. And we're going to use something that is something like 1 over 1 plus tau. So what's that going to do is it means as I step, I take smaller and smaller steps each time. That's going to converge eventually, because that thing is going to go to 0 no matter what my gradient chooses to do. Assuming my gradient is well behaved and bounded. Details. Okay. So this in principle is going to converge when the gradient to 0. In that nice parabola, when I get to the bottom of the parabola, the slope is 0. Right? In practice, I might get to something where I'm just kind of bouncing around and never really getting to the slope, or getting to the very bottom. And so when the slope gets really close to 0, I might also stop. All right. So we just did gradient descent, and I'm going to tell you that that algorithm is actually pretty slow. We can do better. It's computationally slow. Why is it computationally slow? What's the slow part of this algorithm? Calculating the gradient. Good. So calculating the gradient. Why is calculating the gradient slow? It's just calculus, right? Plus, the computer has to do all the work. All right. So I'm taking the gradient of the loss. In many real problems, in fact, almost all the ones we'll deal with in this class, the loss is really going to be the sum of the loss for each of the data points. If I have 1 billion data points and I want to compute the gradient of the loss, I'm going to have to compute 1 billion gradients and sum them up. And if I made my model like I'd love to, thousands of parameters, so for each of these billion things, I'm going to compute 1,000 numbers, and I'm going to take the sum of these 1 billion times 1,000 numbers. And guess what I'm going to do? I'm going to take a gradient step. Repeat the process again. So that seems really costly. What do we do in this class when we have to make these costly calculations or costly measurements of a large number of records? What would a statistician do? Sample, right? So you're doing the census. That's so expensive. Who would bother to do that when all I really want to get is a rough direction to step, right? So we sample. So you've invented the now state-of-the-art algorithm in machine learning, stochastic gradient descent. So what do? We take our giant population, grab a sample. How big of a sample? Big enough. So originally, the sample could have been 1. What's wrong with sample size 1? It might actually work. In fact, some of the early work in stochastic gradient was just take a random point. Take the gradient. Take a step. If I do this enough, on average, this is going to go in the right direction, right? But, computers are fairly fast. I have parallel hardware. I can improve the quality of my estimate of the gradient by doing what? Taking a bigger sample. So I'm going to take a sample. We'll call it batch size B. So I'm going to take a batch of data. How big should that be in practice? Yeah, you can't answer that question. So it sort of depends, right? A lot of people doing things in computer vision for neural nets, 256 seems like a good number for image data. turns out if I give you 100 GPUs, if you make your sample really big, you can use all the parallelism in those GPUs and boil an ocean. We'll come back to that in a moment. But you can use all this compute power to get just a better gradient, right? So when you have lots of parallel resources, making these batches bigger has a dual effect of giving you a better way to use your hardware and also giving you a better gradient estimate. But of course, there's going to be diminishing returns. I make my sample too big, I'm just sort of wasting time, right? So there's a trade-off that you'll have to figure out on your problem. So draw a simple sample, simple random sample. Okay? And this is called a batch, or sometimes called a mini batch. It's a little mini batch of your data. I talked a little about this trade-off. So as I make the batch size bigger, I get to use more parallel resources, I get a better gradient estimate, but at some point it's kind of diminishing returns. And I use that sample to construct and estimate my gradient, and I take a step in that direction. Is this always going to work? Can I just, any problem, I can just make it a stochastic gradient descent problem. There's a little bit of an assumption that I'm making here, and that is that my loss is this decomposable loss. It's the sum of the loss of each of the elements, so I can take a sample and get a good estimate of that. If it's not, I might have to be a little more clever about how I define my sample. But again, for most of the problems that we'll encounter in this class, in fact, all of them, and for a lot of the problems we'll see in machine learning, this actually is the common case. So I have this giant decomposable loss. Okay, questions? Yes? So I'm sampling, I'm getting noisy estimates, so I might have to take more steps. True. So, and especially I'm taking one single data point. I'm going to be running all over the place, so I try to find the way downhill, right? The thing is, every single one of those calculations is now really fast. So I can just run through these calculations really quickly. I can adjust my learning rate sort of haphazardly until I get to the point where I'm solving the problem. So it is a trade-off. So as I make these samples too small, I slow down my convergence. Make them too big, it's too much compute per individual step. Okay. So two big algorithms we've covered. Gradient descent, stochastic gradient descent, they look very similar, right? The big difference is we've brought in this idea of sampling. And with sampling, we can go much quicker. All right. I want to give a pictorial view with animation of what it means to run both of these algorithms. So again, I'm in parameter space, so I'm traversing not the space of my data. This is actually 1D data, perhaps. So this is like I'm fitting a linear model, right, with slope and intercept. Well, let's call the intercept is going to be theta 1. Slope is theta 2. Okay? What I'm visualizing here is the loss surface. If you're looking down on it, so I'm drawing contours. The dark area is the bottom of the loss. The light areas are the top of the loss. So I'm trying to get to the center of this bowl. If I start with my initial guess here, and I take a gradient, you might say, go that way, right? So I take another step. So I'm moving through parameter space. Each point here is a new model that perhaps better fits my data. Hopefully, as I walk through this space, better fits my data. And you're noticing with gradient descent, I'm making pretty smart decisions about which way. In fact, for my given point, I'm finding the direction, at least, that is the steepest descent direction. Right. And notice here, the step size is getting smaller, in part because maybe the gradient is getting a little flatter. Also, maybe I've set this 1 over t+1 learning rate, so I'm forcing myself to take smaller and smaller steps so I don't overshoot. Of course, you're starting to see a problem. If I make it too small, man, it's going to take forever to get all the way over here, right? And then we bring in stochastic gradient descent, and it goes, hey, I think the gradient is roughly this way. Great, so I go that way. And then it goes, you know what, looking at this point and taking maybe two example data points, I think the gradient is this way. Right? But the cool part is I'm making these decisions much, much faster. I'm not looking at all my data. Right? So I'm going to bounce around a lot more. Sometimes I bounce entirely the wrong direction. Why would that be? Maybe I take a single data point that doesn't agree with the rest of my data, and it says, hey, go this way. So I follow that data point. Right, so noisy gradients can hurt. They might take me in the wrong direction. But hopefully, on average, I'll bounce when I get to the bottom. Right. Little side note. If this thing wasn't a giant, nice, clean bowl, as is illustrated here, and there's little pockets of good solutions somewhere, which will happen when you start to do these kind of neural nets or more complex models, this variability actually becomes useful. Because sometimes maybe taking just a random jump in the wrong direction gets me out of this little bowl and maybe moving in the right direction. So what you will see in the adoption of stochastic gradient in these really complex problems today is that it can really help. This extra noise can actually be useful in getting out of or getting unstuck in these local minima. Yes? Of course. So, man, you're running along, and you found the minima, and you take that one data point and just walk off, and you've lost your minima again. I wasn't planning to cover this, but so what kind of happens is I actually want to find minima that are really big basins. If it's like a tiny minima, it means like, hey, if I just move to the right, my model's terrible now, right? So I want a minima where, like, if I just, I can walk around comfortably and it's not really affecting my answer.